heat naturally, as well as the heat that we are generating, in the sense we are pumping up the greenhouse gas for the last 200 years, due to which the atmospheric heating increased. But are this heat staying in the atmosphere? Probably not. Maybe ocean take up a huge part of it, and how much and how is the ocean going, is regulating or mitigating naturally the climate change that made by us, is what I am going to introduce. And then finally, role of oceans in climate change, which is basically containing all this. So, with this small introduction of contents, let me move ahead. Oceans is a very preliminary geographical introduction. This is a time for you to refresh about the oceans. Probably you left this figure in your school. 70% of the global surface are covered with oceans, okay? And there are 5 major oceans, as you see in this. Some of this language may be of my regional language, because the slides I copied from recent talk I given to my regional place. Okay. So, some of the so this is how the global ocean is distributed in a Cartesian coordinate system. So, you can see the major one is the Pacific, which is north south, and it is cut by 180-degree date line. What so important about Pacific is, if you look at the globe, the sphere, the half of the globe is Pacific Ocean. It is so huge. Okay. And then the next one is the S-shaped favorite ocean, Atlantic, the second largest. Then comes to the Indian Ocean and the Arctic and the Antarctic. So, this is how the global oceans are distributed in the Earth's surface. Okay. So, now let us see how, I do not know how many of you know this. Let us go into the depth of the oceans. This is what you will see. Okay. The ocean starts from the beach. Of course, I know all of you have been to beach for your fun. So, from the beach towards the ocean, it is roughly 10 to 100 kilometer in width, and where the slope change 1 in 200, that means that that part is called the shelf. Okay. Shelf width or shelf depth approximately reaches up to maximum up to 1 kilometer, no sorry 200-300 meter, the shelf depth as you reach up to the edge of the shelf. Then there is a sudden slope towards the abyss of the ocean, and that will go all the way up to a 4 kilometer on an average. That is the depth of the ocean. So, you can assume how big is 4 kilometer, because you know the kilometer in distance horizontally, you travel 4 kilometer day to day you travel, right. So, you can assume how deep is the ocean, and the ocean floor is quite dramatic. There is a rise after the slope, and then there are mountains and trenches and even islands. Okay. Some mountains pop up as islands, and this is how the ocean geographically look like. And this particular shape has lot of importance in the way the way ocean behave, especially dynamically. You know, this is just fluid. Okay. The fluid is at a different thickness and set to motion. The range in the changes in the thickness will add additional components is dynamic. So, that is why the relief of the ocean floor, we call it topography, is of a critical importance. So, this is how geographically how we can describe how the ocean cross section look like. So, on an average, ocean is at depth of 4 kilometer deep. Now, let us get familiarized with some of the most fundamental characteristics of the ocean. Start with the physics first. If you look at the temperature of the ocean, those who are not familiar how ocean temperature is distributed, you can see in the tropical, that means roughly 30 south to 30 north, the surface temperature is roughly 30 degree or 28 degree warm. And then you see, do I have a pointer? It is all right. So, then you see a region up to which the temperature remains more or less the same, and there is a sharp decrease in temperature from 30 to 10 degree, happens somewhere around 300 to 500 meter. So, you may think, why is this happening? Why the profile of water temperature changes in this particular fashion, or you should also think what maintains at this equilibrium. Yesterday there was Mimamsa critical thinking problems where radiation balances were discussed. Perhaps that has something to do with this type of balance as well, but in the water. Okay. Then you see a region from 500 to 2.5 kilometer, more or less similar temperature, okay, with depth, and this is the profile of temperature structure within the ocean. Okay. Characteristically it looks simple, but this asymptotically approaching shape should tell us something is in balance, which maintains this, which is not collapse, which is responsible not to collapse this particular structure. One thing probably you know that if you have a warmer water at the surface, it must be less dense, maybe the stability of the system may be responsible to maintain in this way. Anyway, this is an interesting point, I will come back to this later. Then the second most important, we all know that the ocean is salty, right, and I will ask you a question why it is salty. So, ocean is salty in the sense we call saltiness or salinity is the term we call, which is roughly around 35 grams of salt in every kilogram of water. That is what you are going to get. If you take 1 kilogram of water, evaporate, you get that 35 grams of salt in it. Okay. So, structure of salinity is not very dramatic in just like in the temperature, because the range is very less. It ranges from 31 to 34 or 33 to 35. It does not range much. That means ocean is well mixed in terms of salinity, but not in terms of temperature, and that consequence to the density is what going to see next. Before that, another physical important characteristics which influence the life in the ocean is the light. Why light is so critical for life? Nobody living just for the light for reading a book there, right. There are planktons which depends on light to photosynthesize, which is a fundamental producers in the ocean, right. And these planktons get light not at great depths, up to 60-70 meters, light is cut off by 1% of its surface value. Oh, light is cut off up to 1% its surface value. That means we have 100% light at surface, you just get 1% light at a depth of 60 meter. That means below 60 the ocean is more or less dark. Okay. If you have a dark ocean, the planktons cannot function. That is an important part how the biology survives within the ocean. Going ahead, so this is the sea surface temperature. For those who have not seen this map earlier, several questions you can ask, who measured it, okay? How did we get this information? Think about it, I am not going to answer it, or you can Google it. So, this is the sea surface temperature, a very interesting pattern like a painting. So, this if you look at the tropical region, which is between 30 north to 30 south, you have warm water sitting especially in the Indian Ocean and the half of the Pacific, and the remaining half of the Pacific is relatively cold, and Atlantic also kind of warm in the tropics. Okay. So, interesting pattern, and the most recognizable pattern is the contours are running east west, they are not running north south. You can think why, right. So, these are some critical thinking questions, why the structure of ocean temperature runs east west, not the north south. So, probably simple answer would be the spherical surface, in the tropics you get surplus sunlight and the earth rotates east west. So, it receives the sunlight equally in the tropics. So, and less light in the mid latitude. So, naturally the water will be warm in the eastward direction uniformly. So, the contour should run naturally east west. Another thing that you can notice that the ocean is as cold as 2 to 0 degrees centigrade, but it still does not freeze because of it is high saline. So, it can still survive below the freezing point because the salt separates the molecules not from freezing. So, you see roughly 2 degree to 0 degree centigrade in the polar region. So, this is how the temperature of the ocean looks like. And then comes the saltiness or the salinity. Salinity also shown here, you can ask who measured it with this precision and these features, these many features, right. This is measured by satellite. Think how satellite can measure saltiness in water. Satellite is 300-400 kilometer up above you, but it can sense the saltiness in the water in the ocean. Interesting, right. Should think about how they do remote sensing of this parameter. Anyway, saltiness has so many things to say. It does not range as large as temperature do, but it ranges between 30 to 35. You can see most of the colors is encompassed within this part, and extremely salt water you see in the Atlantic, but you do not see them in the Pacific. Again a question, why, right? We can ask why is that, why Atlantic is so special, get more salt, but Pacific is more dilute. Indian Ocean, if you look at, it is a mix of both, the west is more salt, the east is less salt, probably not much of a gradient. You can see it may range between 35 to 30. You may ask, is it so important? Yes, it is important when it contributes to the density. Anyway, I am not answering all these questions because we will never end up our talk. Okay. So, I am just posing these questions for you to think and imagine how this is achievable in terms of fundamental science. The question, how did ocean become salty? Some of you may know the answer. So, this is the sequence of events. We hypothesize the reason why ocean is salty, that in the beginning the universe In the beginning of the universe, the earth was a hot ball of molten lava and hot gaseous atmosphere. It eventually cooled down and the water vapor gave way to rainfall. Lowlands became water bodies and the minerals and nutrients which washed away from the land brought finally back into the ocean, because that is where the largest the lowest potential, but the strongest stability achieved by all minerals, and it arrived at the water bodies which remains close to the earth's surface due to its restoration by gravity, and it is fluid, it is not solid. So, the minerals and nutrients arrived in the ocean, and many nutrients being used by the life, the biology within the ocean. Some ions left behind, say sodium and chlorine for example, they combine to form sodium chloride, salt, and that the reason we see the salt today 35. So, that gives you another way of thinking, then the ocean might have evolved in billions of years of time scales, because all this to happen to reach an equilibrium of salinity today, which is 35, is not going to change much except the seasonal changes at the surface due to rainfall refreshing and evaporative hardening. The things are pretty much in balance. So, that means it evolved spending billions of years of time scale, the ocean. Okay. So, that is the interpretation of that. So, that is the reason the ocean is salty today. Now, let us come to the more important physical quantity called density. Okay. So, density is a function of temperature and salinity mostly in the ocean. They are having a nonlinear relation, we can linearize as well. Well, what about density? So, this is a typical density profile. I draw like a cartoon. Ocean density first of all is larger than freshwater density. Why? Because of the added salt. So, the extra weight is there, right. So, it starts with somewhere 1020 and goes up to 1025, 1030 or 1035. That is the density. Usually, we subtract this 1000, we talk about 20 to 35 range. That is what oceanographers do. And you see in the surface the density is less, and then suddenly density increases with depth, and at about 300 to 500 meters, then density monotonically increases in a small manner. So, this answers the question, the ocean is stable because the low density water reside on the high density water. If you look at the right hand side, which is a cross section of the ocean from 60 south to 60 north, cutting across the north south direction, looking at the depth, you see the isolines of density quite like this, and this is the most stable structure. Why? Given the condition, the density monotonically increases with depth, rho 1 less than rho 2 less than rho 3. So, for any density larger than the density above of the water above, it is a stable condition, right. The other way it is a unstable condition. So, ocean achieves stability by this way of aligning its density, and that is achieved how the temperature and salinity is distributed within the system. Now, why are we so critical about density? Actually, density is not the way as it is shown in the previous map. When you measure the density of water, you get a line like this, because the water is pressurized as you go down, which influence the density. But is it the actual density of the fluid? No, it is due to the pressuring. Suppose you bring that parcel from 1000 meter to surface, what its density would be is its potential density. Other densities are density by the pressure. So, we oceanographers usually look at the potential density, which is what I show you in the previous slide, that a water brought from any surface to the any depth to the surface adiabatically, not giving any time for it to exchange its internal properties, then what density you would get is its potential density. Anyway, if you either look at the actual density or the potential density, you get a structure that density increases with depth, and that is why the ocean is stable. Okay. So, these are certain physical characteristics of the ocean we are going through. Now, why I mentioned this density is that before going further, let us see the density structure of Pacific Ocean as by the observations. Okay. So, what is shown here is southern latitude 60 degree south, equator and 60 degree north. That means, it is a north south section and a cut in the ocean from surface to 6.5 kilometer depth. So, these are the bottom relief or the mountains in the ocean, okay, or the bottom surface, so bottom topography of the ocean, and there is something pop up here. This must be a part of island, right, in this particular trajectory. This must be taken from a ship observation, right. A ship might have sailed from North Atlantic to South Atlantic, measured the density on the way. and then plotted it. You can see very interestingly the larger density resides below and 1000 is subtracted. So, we can see the value 28 here, but 26, 25 on the top. So, this is how the density structure looks like, but this has some peculiar property. If you observe, some density line surfaces as you go south, right. What I say is that, say for example, this density, it is at a depth of 3 kilometer in the tropical region, it is going all the way to surface when you reach the polar region. Why is that? Another thinking problem, something to do with the temperature, right. The colder water will have a larger density, that may be a reason the isoline surfaces. Now, why this isoline surfacing is so important? Because that is an important property how the ocean is controlling our climate, which I can prove with a slide as a skip before the sea surface density. Okay. So, if you have a density structure like this, okay, and if the ocean currents establishes with this density structure, the currents pass along the isodensity surfaces. The reason, because if currents to go vertically, it has to break the barrier of stability, which is quite impossible, because the restoration due to gravity by two densities are quite larger. You need so much of energy to break it, which you do not have in the deep ocean, which we have in the surface ocean by the wind steering, but if you go below some depth, say 50-100 meter below, nobody can break that barrier. So, currents moves along its isodensity, because that is where it finds the stability, right. So, if that is tilted, the currents will go again like this along, okay. It will never cross the barrier of density barriers, okay. So, that is one particular property, this is due to the stability of the system. Now, think about a scenario like this. The ocean currents due to differential densities or density gradients are along the isolines of density. So, what I have shown a cartoon here, this is depth on the height axis, and this is west, and where is my east? That is north. So, that is north, west direction and depth. That is a 3-dimensional structure of density isolines. You see at some point the isolines are surfacing and they outcrop, they open up, and anything enter at that point will slide along. Now, let us, what is entering through those points? Probably the heat, the additional heat, the greenhouse gases what we generate in the atmosphere, they all may get along these surfaces. Once this is surfaced, it is outcrop, once it gets here, and then it has traveled to the depth, which is never accessible to the atmosphere again. And that is the reason we look at the density, because ocean currents are established through the isodensity surfaces, which has a critical role in today's climate. Why? I will prove it towards the end of this talk. So, this circulation is called thermohaline circulation. If you look at the global thermohaline circulation, this is what you get. You see, all the diving of the water happens at the north cold latitude, and once it dives, this is a warm route, and there is a diving at the north. Once it dives, it travels through the south. So, when this diving happens, it was in contact with the atmosphere. It had its heat memory, greenhouse gas memory, and so many memory, and it takes up and dives, and it never brings that back to the atmosphere. So, it is kind of storing whatever we dump in the atmosphere, it gets at from the surface and dive. So, ocean is a natural storage of anthropogenically perturbed signals. Okay. So, that is how the ocean store it, because the ocean circulations are established along the isodensity surfaces, which is a very critically interesting point. Now, this is the global conveyor belt through which the major heat transport in the ocean happens. You can see this is a warm route and goes all the way, dive, and then the deep cold route and return back, and it may surface by the large scale dynamics elsewhere in the global ocean. But this belt brings the extra or anthropogenic information to the interior of the ocean. And how long this belt, how long it takes to complete this belt? Say for example, I start my journey from here through this belt, I come back at this point maybe after thousands of years. It is slow, it is not a very fast process. Okay. And that slowness is what regulating our climate today, because it absorbs it sink and reside there for a long time. It going to surface after some time, maybe not today, 1000 years after, but at least it is helping today, right. So, that is why I say the global climate is regulated by the ocean by its natural circulation. So, this is the typical example of a global conveyor belt. So, now let us see. So, under these circumstances the heat and gas enters from the atmosphere, the purple arrows which is a vertical arrow, that means the atmospheric information is getting trapped in the surface ocean. It penetrates at depths along these density surfaces. So, in this manner the oceans are capable of storing the heat from the atmosphere to interior. Tell me how much percentage of man made heat is absorbed by the ocean today? Anybody know that number? I will give you some clue, 10 percentage, 30, 50, 80. Actually, to your surprise, 90 percentage of the man made heating is absorbed by the ocean. Very humble, huh? But it doing a great job. So, why is that? Because of this isoline density structure and the way currents are established. Nobody told ocean to do that, but that is how the nature evolves. Okay? I will show you towards the end the storage pattern of heat within the ocean. That is very interesting. Let us go ahead. Now, to all this to happen, we have to pass through this humble gate. To enter a highway, you need to pay the toll and get through the toll gate. There is no other way you can get in the gate. So, in the ocean as well, for all these atmospheric anthropogenic informations to get interior, it has to pass through a humble gate called the mixed layer. So, what is mixed layer? It is nothing so dramatic. It is in the surface of the ocean where properties are found well mixed. We may ask why I said mixed layer in the middle of all this discussion of heat storage. Important, it is important. If you look at the, oh sorry for this okay, my regional language. So, the mixed layer is the depth at which the temperature you find uniform at the surface, or the best way of saying is that properties are well mixed, okay, and that is called the mixed layer. It is about 40 to 100 meters of the ocean are well mixed, the so called mixed layer of the ocean. Within the mixed layer, the properties are more or less uniform with depth, and I say why I said this, I will reach that point. How do ocean mix? You can think. Ocean is a steadily stratified medium. The low density, high density, higher density, higher density, higher density can't break the barrier, but still it makes. So, that means it need to have some momentum input from the atmosphere through wind, or it need to have some heat input or heat extract from the atmosphere, right. The first one is shown here, the wind. Ocean is not calm, always under the steady action of the wind. All right, this wind stir up the ocean, a mechanical stirring or turbulence will cause it to mix. That is one reason ocean mix. The second reason is the mixing due to heat exchange or the buoyancy forcing we call. The colder ocean give up more heat at some point of the season, become denser, heavier at the surface, which can't stay there because unstable, it tend to mix. It generate eddies and it tend to mix. There are the two reasons mixing is happening in the ocean. So, turbulence generated within the ocean due to the wind forcing and buoyancy forcing cause mixing. Mixing is a phenomenon through which the exchange of momentum, heat and mass, so many information across ocean air interface happens through this process of mixing. That is why I mentioned about mixing, because we are trying to tell here how the ocean takes up whatever from atmosphere and stores. It has to pass through this mixing area, right. So, mixing is the most fundamental in the air sea interaction. So, let us see some of the signs of air sea interaction, because you can, it may give you some venue to critically think. This is the cartoon of various air sea interaction happens in the ocean. Air and sea are like brothers and sisters, okay, they stay together, or bread and butter. Atmosphere and ocean are not two entities of the earth system, they are one and the same, okay, having two different shapes and structures. So, the first exchange is the momentum. When you have a wind, that is the mechanical energy which stir up the ocean. So, the transfer of energy, how it happens, I will explain slightly later, but for now you take it as this mechanical energy get transferred to the ocean, and that is how the ocean is pushed, otherwise ocean will not move, right. Next is the heat outward, that means evaporation, okay, which cools the ocean, right, and that heat is used for the water to evaporate and it exchange as humidity. This is another exchange process happening at the air sea interface. then heat itself can get exchanged by hot air from the surface can go upward, carries heat of the ocean to the atmosphere, a conductive phenomenon of heat exchange. Then radiation, all bodies radiates proportional long waves or short wave, whichever according to its temperature, by Stefan's Boltzmann's law, you all know. So, a radiation can be another way of exchange between the atmosphere and ocean. Mass exchange, when it rains, the mass is added to the ocean, when it evaporates, the mass is taken away from the ocean, that is another way of exchange. The last but not least, the exchange of gases, that is what today regulating our climate, right. What gas is of our primary concern? Of course, carbon dioxide. How the gas is exchanged? Gas in the ocean, and that gas, if it is not in equilibrium with the concentration in the air, there will be a disequilibrium in the partial pressure, due to which gas can escape, all right. So, these are the various exchange processes at place or in place within the air sea interface and this has to go through the some fundamental area called the mixed layer, or in the atmosphere we call it boundary layer. Okay. They are the same phenomenon, but having different structure. Now, let us look into how the momentum exchange happens from the atmosphere to ocean. Fundamentals of air sea interaction. How does the momentum get exchanged? So, if you have a wind moving or blowing over the ocean, due to naturally due to friction, there will be a retardation at the skin as compared to the wind aloft, which make a sheared layer of flow, and whenever there is a shear, the momentum is exchanged across the shear, right. So, through the turbulent eddies, therefore, the momentum exchange, momentum is rho times u or mass times u, the zonal moment or the horizontal momentum, it exchanged across and this momentum causes the shear of the wind, which is dou u by dou z. That means, the net transfer of horizontal momentum in vertical direction, a w component will come, which is downward. This is the momentum, this is the mass rate of flow. Okay, I am sorry, this is the mass rate of flow, and this is w, which is momentum, is proportional to the shear established. All right, or in other way of saying that, by the principles of frictional flows, the stress experienced must be proportional to the shear of the flow. What is the shear I am talking about? The shear of the flow within the ocean. This is atmosphere, this is ocean, right. So, the stresses must be proportional to the shear of the flow, and that you can equate these two. So, that means tau equal to rho u w, that is the wind stress or the exchange of momentum from the atmosphere to ocean. W is a bit tricky to estimate, therefore, let us transform w in terms of u. U is easy to measure, w is very chaotic. You can do that, but a sufficient approximation, putting a coefficient called drag coefficient, again parameterization comes. This is where the uncertainties jump into the system. Up until then, theory was good. The moment you put proportionality constants or any constants, the parameterization jump in. Whatever it is, the stress experienced or the exchange of momentum per unit area must be rho c d u times u, where u is the wind speed. So, this is how the atmosphere exchanges its momentum to the ocean. Once it achieves the momentum, it starts to move. That sets our global general circulation, right. Ocean is not a steady medium, it is constantly under movement. Are you guys with me? I hope so. Now, let us take into the account the next exchange. How do ocean exchange water vapor across its interface? This is one example. What happens is very interesting. Close to the skin, the water vapor of the air is at saturation level, because it is close to the skin, it can derive water vapor any time. But if you go aloft at 10 meter, it is unsaturated vapor. So, there is a concentration gradient of humidity, right. And if you have a wind blowing on top of it, what happens is that the turbulence sets in, will bring this air upward and this air downward. So, on an average, there will be a net transfer of moisture from one side to the other side. Turbulence is something that kills the gradient, it does not like the gradient. Why turbulence happens? To kill the gradient, make it background, all right. So, the humidity get exchanged upward, or the moisture get exchanged upward, and this is one way of exchange of mass in the air sea interface. Usually in mathematically, we can calculate the latent heat of evaporation in the terms that I have written there, in which u is a critical parameter. If there is no U, which is wind, no turbulence, there is no upward upliftment of moisture. So, U has to be there and there has to be a gradient. If gradient is 0, there is no upward movement of gradient of what? Humidity at this height with the humidity at this height, the gradient. If no gradient, there is, that means it is already well mixed humidity structure, right. This is another way of, this is exactly what happening when you blow a cup of tea to make it cold, right. You put more wind, you take more molecules out of it, right. But here it is not any more molecule, rather you replace with eddies of large chunk of molecule, just like that. Now, heat itself can exchange as a conductive mechanism. This is the air which is heated at the temperature of the sea surface, and this is air at a different temperature from the sea surface. Whenever there is a gradient and eddies, it can exchange the heat as a conductive heat. Just the air heated up from here rise upward, or it can the other way also, atmospheric heat can comes to ocean also, right. In both the way it can happen. This is how we call it sensible heat flux. Okay. And the last and the not the least is the radiation, which is very important and funny. As I said in the beginning, light penetrates maximum up to 60 to 70 meters. Below that, light is cut. That means the light is absorbed within that depth. Okay. So, light has higher absorption in the first few meters. So, this is atmosphere, this is ocean. First few centimeters of the ocean, this is what happens. It gets heated up and long wave started emitting in both the direction, but long wave is highly absorbent in water. It cannot escape, okay, at certain depths, and it get trapped within it, and from the skin long wave can emit. Okay. So, from the skin long wave can emit, and some radiation, this is short wave, okay, it reaches the some depth of the ocean. So, this is the radiative heating within the ocean. So, the net balance in heating of the ocean column must be the balance between the incoming radiation, outgoing radiation, a heat exchange, or the heat due to the exchange processes, sensible, latent, etc. Right. So, this is the how the air sea interaction fundamental works. And the last, how the gas is exchanged. In the same principle you can examine when the wind induces shear in the wind, and there must be turbulence, and the turbulence carries the water, the air which is close to the surface of the ocean aloft, it carries upward, and this air must be in a gas equilibrium with the water, because gases are soluble in water according to temperature, condition, etc. All right. So, the gas can exchange, and for example, in the CO2 we call it exchange as a function of difference in partial pressure of that gas with respect to the ocean and the atmosphere. Okay. Every gas dissolved in a medium experience its own pressure. If when that pressure exceeds from one medium to the other, there can be an exchange of carbon, right, and that exchange is what taken up, exchange is what helped the ocean to take up the amount of CO2 we emitted to the atmosphere. Can anybody tell how much of man emitted CO2 taken up by the ocean? Heat was 90%, it was quite surprising. Let us see how much carbon emitted by the ocean as of now. Since the industrial revolution 1870s, the CO2 is increasing. How much of that absorbed by the ocean? 10%, 30%, 50%, 80%, much more, actually not, unfortunately 30%. So, there are differences the way heat integrates into the system and carbon integrates into the system. That is all happens because of the different exchange processes they have, all right. But 30% is still good. What is the emission of CO2 today by man? As in every year in the today's world, we emit around 10-11 petagram of carbon per year. Peta means 10 to the power 15, it is a big number. That many gram carbon per year we emit by fossil fuel burning, cement production, industrial activities, and so many other. Out of which the ocean takes up 30. That ratio is pretty well maintained. That means around 2.5 to 3 petagram is removed. Okay. Terrestrial biosphere, they are not silly, they remove another 2 to 3 petagram extra, they are also removing 30%. So, what we see today in the atmosphere is after those removal. Now, think about a scenario, these two guys are not absorbing, the accumulation of carbon today would have been double or several other fold, and the global warming would have been in a different rate today. So, that is why we should appreciate the role played by the ocean in regulating our global climate. Let us talk about not much theory, let us talk about some of the observational efforts also. Unlike other sciences, the observation of earth system is very difficult, can't do it in a laboratory, you have to go to field. Okay. This is how the ocean is conventionally measured for last 60-80 years, or early explorers from the European region to the other continents. This is how they explore the ocean. They go on a cruise, we call it scientific cruise, and they make measurements with their available instruments of the properties of water, say it be temperature, salinity, dissolved oxygen, or whatever nutrients, carbon, okay, whatever they can measure. So, even today it is one of the most important observation methods in oceanography. We still go for cruise, even though we have modern technology such as this. Have you seen this map earlier? If you have not seen, it is a chance to see. What are shown of that dots are autonomous floats. These are engineered floats, looks like a cylindrical tube of height of almost about my height, all right. And these tubes, when they throw, it fill up the ballast and sink. Pressure gauges controls the ballast, so that it sinks precisely up to 1000 meter, where the ballast closes, no more sinking. And during its descent, it make measurements of temperature, salinity, and whatever other parameter it can have, because they are electronic measurements. Modern day technology is much different from conventional oceanography, right. And after spending 10 days at 1000 meter, the valve opens, it releases the water, it start to ascend, it comes back to surface. Again it make measurements of those parameters very precisely at those steps. After reaching the surface, it communicates to the satellite, and satellite will transmit the data to ground. These are autonomous floats. How many are there? 3900 floats are placed. These are free floating floats, okay. They move with water, they are not at one place, they are just freely floating objects. These are called Argo, which revolutionized the ocean observation today. That is why you are having a high accuracy in the weather prediction today. You can say when a cyclone is going to come, because so many data is collected by these autonomous instruments and telecasting to you, which uses in your simulations to improve accuracy of any weather prediction which is happening today, right. That is why we do not see a wrong prediction of cyclone anymore in the news. We know, we celebrate cyclone in social media these days. We know where it is going to happen, and the media will chase the cyclone, right. The landfall is going to come today, tomorrow, NDMA is working, and the evacuation is going on. So many things happening because of so much data came into our hand. And this is a floating Argo, okay, and this is the principle, and this 1000 meter, then some dives even 2000 meter, it is ascend and descent, and it make measurements of temperature and salinity. These floats are free floating objects, and although they occupy a significant space in the map, that is not to the scale, okay. Each black dot is so big in the map, but the float looks so tiny, okay. So don't think that when you go to ocean you may gonna get hit with some Argos, no, not like that, okay. All right. So but fishermen sometimes encounter these floats and they catch in their net and they throw, or sometimes they report it back, sometimes they hide it, sometimes they throw next time and they go, but anyway it is not useful, okay. So this is the modern day observations, Argo float. Next is buoys, moored buoys, and these guys are very important because these are stationary, unlike Argo, they move around. I am exceeding my time, can you bear with me another 15 minutes, 20 minutes? I do not know how much I can go in this small time, but anyway. So these are the buoys, and these are moored in this fashion, and instruments are attached to this, and we can get data. That is the actual image of a mooring. And in the Indian Ocean we have several mooring places, and the job of these guys are to look at the weather of individual place and give us the yes. Then comes the satellite. These are all modern day technologies of measuring the ocean, right. Satellites are up there either in polar orbiting or geostationary, and they remote sensing technique. One of the advanced physical or physics technology engineering meet together. They make measurements of all the parameter whatever they can do and give the data to us. So there are billions of data points per hour or per day is generated by all these observational effort and transmitting to us, which makes our weather prediction very accurate in these days. Coming back to the ocean, This is how the ocean circulation is established. You can see various red colored lines. Ocean is not a stable medium, it moves around. You can think why is it moving, okay, etc., etc. I am going a little fast now. And the ocean, the atmosphere, sorry, the earth system is a rotating system, right. So, in addition to the forces that you are familiar in your laboratory, right, the pressure, stress, right, viscous forces. If in a rotating frame there are additional force called Coriolis force, right, that also play a huge role in the circulation of the ocean, which is demonstrated here. In a rotating frame, in a disk, there is a tendency particle to veer to the right or to the left according to the angle of or the rotational direction. Okay. So, in this particular there is a tendency to steer to the right when the particle is in more the fluid is in motion. So, this is called the Coriolis force. I am not going further into this due to lack of time. Atmosphere is an well, or ocean is an well, it is a very good example how the Coriolis force is in effect. When there is an air parcel tried to move, it drifted to the right in the northern hemisphere, and the more accurate depiction is that in the 3D, if you look at a chunk of fluid which is that red bread kind of shape I have shown, in from space if you look at that chunk of fluid, it is under the rotation of omega sin theta, where omega is the rotational frequency of the earth, which is 0.729 per second. Okay. Now, what is the consequence of this? There are some interesting dynamics established within the ocean called Ekman currents. The first few meters of the ocean, if the wind direction is in that, it tend to move in that direction, but it rotates with the depth. Eventually, on an average, the ocean moves 90 degree to the wind. This is another weird aspect of the ocean. The wind blows this way, the ocean goes that way, right, but it does because of the Coriolis rotation of the earth, because these are large inertia system. Mass is so huge, even a small velocity will make a large inertial system, right, and it has a tendency to move to the right hand side in the northern hemisphere, which altogether sets up this kind of circulation pattern I have shown earlier. This is called gyre circulation, which is why I discuss this here, carries the warm water from the tropics all the way to the north, and this warm water interacts with the atmosphere through air sea exchange process, and the heat gets forced into the atmosphere sets into motion, and the same atmosphere forces the ocean. So, this is a coupled system, it is not like a standalone system, all right. Going further and coming back again, climate and heat and ocean. This is a plot showing the total heat storage or heat capacity Hc, which is an integral of density, specific capacity and theta. Theta is the temperature and integrated with depth. This is from the direct observation, and this integral is for the global. This is a volume integral. Okay. The heat capacity of the ocean from the 1960s, if you compare, take the difference of the heat capacity from 1960 to today, the heat capacity increased. That means the ocean is accumulating more and more heat, and this is what I was trying to tell earlier. Ocean naturally takes up the heat from the interior. And if you look at the various depths of the ocean, say up to 300 meter, up to 700 meter, up to 1000 meter, you can all those depths you can see ocean heat has been increased systematically since 1950. Okay. This is observational truth or observed data. How ocean takes up heat? Revisit the mixing problem earlier. This is the mixing problem. This is equator, density isolines outcropping at the high latitude where mixing happens in the winter, and in the summer what happens? Mixing recedes, a layer of fossil is generated. This guy has nowhere to go, it has to be pushed along the density surfaces, and that fossil layer has the information of the heat in the winter. So, every year this is happening, right, and this get injected to the interior, and this is the observed delta T of the ocean. What is delta T? The change in heat or change in temperature of the ocean in the last 50 years is what shown there. You need my help to interpret it. This is Antarctica, this is shown upside down sphere. Okay. This is Antarctica. Each leaf represents each ocean. Atlantic from surface to 2 kilometer depth, from south to north. So, this leaf you can see how much delta T increased in the Atlantic Atlantic Ocean. The delta T is not monotonic, it has some shapes better interpreted in the Pacific panel. This is the Pacific panel. That means it must be zonally averaged and a section. Pacific panel, the additional heat has this type of shape, which is exactly I was trying to draw here. This is the heat inversion, and that is accumulated here, extra heat. Indian Ocean going that leaf, you can see this is the north and this is South Indian Ocean, again the same shape of heat accumulation. And this density structure is of critical, this is what I was starting in the, so saying in the beginning. We need to look at through these fundamental structures of the ocean to interpret how things evolve. This is modern day climate. Let us go now back to a million or a billion years back in time, what ocean did, okay, to the atmosphere. Let us see that again, which is the reason of this. For to see that, let us start with this pyramid. This is a very useful pyramid. Storage of carbon Earth system elements, starting with atmosphere. If you put together methane and carbon dioxide, around 760 gigaton. Gigaton means petagram. Giga means 10 to the power 9, ton means 10 to the power 6. That many gram of carbon is available in the atmosphere. If you integrate all the atmosphere into one value. Next comes the oceanic dissolved CO2, which is 740, almost in a balance. Carbonate ion in the ocean, which is also a carbon storage, 1300 gigaton, it is slightly increasing, right. Then comes organic carbon in soils and sediments. Fossil fuel contain 4200 gigaton carbon, which is what we are now digging and taking up and burning the same amount of carbon, not the same amount, the amount proportional to our digging comes back. Then comes oceanic bicarbonate, 37,000 gigaton carbon compared to atmosphere, which is 740. So, ocean contains several fold, maybe 50-60 times higher carbon than the atmosphere. The question is, where did ocean get this carbon from? That is the question we should ask, and if you answer that, you see the role ocean played in regulating our climate as we see today. Okay? That is what I am going to present next. Some intriguing questions are, compared to the why CO2 in the ocean became much larger, that is the question I am asking. For that, there must have been some CO2 in the past in the atmosphere, right, otherwise ocean will not get this carbon, right. From the beginning, ocean was formed by just the rainfall, which is pure water. But to get carbon in it, it might have brought to the ocean by some mechanism. Let us see that. For that, let us go to a half a billion years past in time. This is a geological calendar. Geologists recognizes these words, and we are today actually in the 10 million of the Miocene, Pliocene, Pleistocene. This is our human evolution happened, and perhaps this is our climate evolved in the Paleocene to today. This is what the modern climate might have evolved, and this is the calendar for the geological events in the past, which is half a billion years ago, where eradication of life happened systematically, especially the KT boundary, probably you know, Cretaceous Tertiary boundary, where meteorite killed all the dinosaurs 65 million years ago, right. Anyway, why I am putting this into context, because to answer this, what was the composition of atmosphere in the early ages? It was hypothesized that very less nitrogen and extremely high amount of carbon dioxide. And today nitrogen is grown to 78 and carbon dioxide reduced it to 0.04. Why they hypothesize this? Because there are evidences to prove it and how we prove it. That means in the early atmosphere, carbon was 2000 times larger than today, 2000 times. We are just worried about a 100 ppm increase in last 200 years. It was 2000 times higher. If it is that much higher, then why did the Earth's greenhouse effect was not hostile to life in early evolution? Another critical question for people from non-earth science background. There must have been something kept the life as it is we see today, or not in the same form, at least for the microbials, right. What kept the atmosphere in a balance? Apparently, the sun was also less bright in the early evolution of the Earth due to the less and less nuclear fusion reaction happened, which we call it Faint-Youngson paradox. I think you probably know this Faint-Youngson paradox, some of you probably heard of it. How does sun generate its energy? Inside the sun's core there are fusion combining 4 hydrogen into helium, and the remaining mass is emitted as energy, which is light on radiation. Due to this, radiation pressure inside the sun increases, and pressure is proportional to temperature, more fusion. So, this is like a positive cycle, and the sun is getting brighter and brighter from 5 billion years to today. That means, sun is now, it was 30% less luminous by the calculation as compared to today. That means, the sun was getting hotter and hotter. So, the question is that if the sun was 30% less luminous at that time in 4.5 billion years ago, what supported the temperature to be favoring the presence of life? There was evidences that life was there at least 3 billion years ago. So, there must have been some temperature, and for that, for a 30% less luminous sun, you indeed need a lot of CO2, not at a proportion 30% higher CO2, because yesterday I asked, CO2 does not absorb in all bands, it has very selective small absorption band of radiation. So, you need to pump up a lot to trap that many heat with a less dim sun, right. So, that is why we say that early atmosphere might have had large amount of CO2, and the question, so this is a Faint-Youngson paradox. In order to support life with a faint young sun, it needs much CO2 than today, and indeed it was there roughly 2000 times higher CO2 in that day, which is the Gaia hypothesis itself says that the earth is a self regulating system in which biota play an integral role. The biota manipulate. I am saying about biota, I never talked about biology so far. So far I was traveling through physics and a bit of chemistry. Now I am coming to biology. The biota manipulate their environment for their own benefit or also optimizes it for the life around it. That is Gaia hypothesis. Okay. So, in that hypothesis it says that the sun was getting brighter and brighter, at the same equivalent proportionate amount CO2 was going lower and lower. And who did this trick? And that must be biology, and biology might have extracted those carbon from the atmosphere, deposited to the ocean. It may look dramatic, but it is scientifically proven and it has evidence also. How did it work? Chemical weathering of rocks, a simple mechanism. Rocks are basically calcite, dolomites and silicate minerals. So, rains are under attack, the rocks are under attacks of rain, and rain weather the rocks and it can release carbon dioxide, okay, and this rain brings weather the rocks and bring these ions to the ocean, say such as calcium, silicon dioxide, carbonate, bicarbonate, etc. And why is it important? Because within the ocean this is what happens. The first is called the land weathering process, which basically looks as if calcium carbonate rocks attacked by the acid in the rain, which is carbonic acid here, it can be any acid, and generate calcium ions and bicarbonate, and this calcium ion and bicarbonate combines in the ocean, we call ocean precipitate. Who takes up calcium carbonate? The planktons for their shells, they eats up the carbon, they encapsulate in their shells and then sink down. This is what they do. So, in the land weathering brings this calcium here, and in the ocean it combines with the bicarbonate and precipitate within the ocean, down the ocean, right. This we call it carbonate weathering. The next is the silicate weathering, which much more interesting. Calcium silicate rocks by carbonic acid releases this many, this is plus, I am sorry, and this reacts with within the ocean, forming the shell formation calcium carbonate, shell of what? The planktons, for example. And the net reaction is calcium silicate in the atmosphere or the land combining with atmospheric CO2 becoming calcium carbonate shell in the ocean. This is an extraction from the atmospheric CO2 to the ocean, and who does? The biology. And the time scale involved is quite large, roughly 0.03 gigaton carbon per year removal is kind of very slow process, but it is a systematically interesting process. This perhaps might have helped to bring down the atmospheric carbon at the right amount. The sun was getting luminous. They all evolved because that is how nature works. It has its own remedy. Even perhaps what we doing to the climate today, pumping up so much carbon, there may be a removal mechanism waiting by their system. Nobody knows, all right. So, this is interesting. I conclude here. I think I did justice to say ocean is important. By saying this conclusion, ocean absorb 90% of the man-made heat and 30% of man-made CO2. They are not in proportion, but they are in the right proportion. Okay. Ocean absorb the atmospheric CO2 and store in its interior systematically just at a sufficient amount to sustain a climate suitable for life, and ocean was an integral part of the Gaia hypothesis indeed, and therefore, we say global oceans are the controllers of today's global warming as well. And with this I conclude, and thank you for listening to me. So, do we have question answers or? There is a question.
So, if you take this conveyor belt slide that you had, and you had a more integrated slide with different currents, if you overlay that on the salinity map, which had different pockets of salinity, is there an explanation?
Well, global conveyor belt will not match up with those circulation pattern one to one, there will not be a match. But circulation and salinity may match, because circulation bring high salinity water to the low salinity area and low salinity water to the high salinity area. So, conveyor belt and circulation may not match one to one, but salinity and circulation may find some match.
Why hasn't it equilibrated? Why isn't the salinity uniform?
Good question. Who forces salinity? The rain. So, the atmosphere forces this ocean through rain only at certain pockets, not everywhere, not uniformly. So, there are areas where surplus rain, there are areas where surplus evaporation. So, there is a gradient always, it can't be equilibrated as a uniform value. It is because the forcing from the atmosphere is differential forcing. If the atmosphere rains everywhere equally, then the scenario what you said will come. Yeah, salinity has a source function from the atmosphere. If it rains, salinity dilutes. If it evaporates, salinity enhances. That is why Atlantic had more salinity, because evaporation is larger there. Pacific has less salinity because precipitation is larger there. The reason why Pacific precipitate more, which is due to this. This is the reason Pacific precipitate more. To precipitate, you have to convect the air from below to up to make clouds. To convect, you need to force with so much heat, and where is the heat accumulated? In the Pacific and in the Indian, not in the Atlantic. So, Pacific rains by convection, we call it intertropical convergence zone, where there is a lot of rain belt here. This is actually the pattern sharing with rain. The higher temperature, the higher chances of rain. That is why Pacific has more rain as compared to Atlantic. So, Pacific salinity dilutes, Atlantic salinity hardens because of the differential forcing, and the very forcing sets by the very ocean. That is why we call it coupled system. All right. Yeah.
So, you had mentioned the thermohaline cycle takes information from the atmosphere, like heat, gases, and carries it deep down to the
Right.
for thousands of years.
Right.
Isn't diffusion of this heat and gas like a faster process than thousands of years? Wouldn't it diffuse away and that information be lost when it's somewhere?
It won't diffuse, because I don't know what diffusion you are talking about. Is it a kinematic diffusion of the fluid or the eddy diffusion of the ocean? In either way, they do not diffuse and equalize the concentration. The reason, because the diffusion amount is much lower than the circulation amount, and that is the reason we have a steady equilibrium of temperature. Otherwise, this should have been diffused and make a uniform temperature. It is not. The one reason is there is a heating from the top and there is an upward movement of water from the bottom. If you balance, you may get an hyperbolic solution to the temperature. That is why the balance is maintained, where diffusion has no much role. Diffusion has role, but they do not act to crack or to collapse it. Yeah, gradients are still maintained, diffusion can't break it. and it diffuses especially along the density surface rather than across the density surface. It may quite weird also. Actually, diffusion we mean should happen across the gradient, not along the gradient, but the stratification will not permit that to happen. At molecular level it may happen, but they are too tiny, 10 to the power minus 7 per meter, but ocean is of so many kilometers in size, so they do not match up. Yeah.
You said that any carbon that is sequestered now in the ocean might be released in the atmosphere of the order of 1,000 of years.
Yeah.
So how do we know, like for our current climate models, that there is not some like unidentified carbon source that is already in the oceans that is contributing?
In the current climate models, the state of the art models are run only for 100 years from today, and they do not resolve the phenomenon that you are talking about, return of the carbon. They do not resolve that, but there are models which low resolution run at a millions of years of time scale, but they do not have that process to return the carbon. So, it is a puzzle. It is certain this carbon has to return at some point. If you look at the interglacial warm and glacial period, if you remember, how did that happen? We were not there. There were several ice ages we passed through. There were no industry that time. Carbon was high, carbon was low, who did it? It is the return of the carbon from ocean to the atmosphere, atmosphere to the ocean. Naturally it happens. It is going to happen in future also, but only exception this time is we pumped up fossil fuel back to the air from the pyramid. If you look at the pyramid, we made a bypass, and we do not know what that bypass going to do. Yeah, this is the best answer I can come up with. Yes.
Could you please explain the third case of coherence force? If it does not take
I do not think it will take time, unless this is what happens now. This is earth as a cap, half the hemisphere rotating at omega. Because it is a sphericity, when you resolve omega, omega is a vector, when you resolve it will have a 3 dimensions in Cartesian coordinate. So, one is omega x, which is along this, and omega y along north, and omega z penetrating perpendicular to the surface, and that omega will be of this direction, which is not omega, omega sin theta, theta is the angle from the perpendicular, and this omega is a reduced omega, because sin theta reduces from 1 for any angle. So, reduced omega circulating in this manner. Why is this critically important? This is paralleling with the horizontal circulation of the atmosphere. So, they are in match. That is why that component is critically important, omega sin theta. And if a guy looks from space, even the ocean is not moving, the frame is rotating due to the rotation of the earth. But the guy has to move along with the earth, okay. The guy should not be geostationary, he has to move along. I mean, the guy has to be geostationary, then only he will see the frame is rotating, yeah, right. Yeah.
Thank you for coming, and I would like to thank the audience. We would like to felicitate you with a small token. Professor Madhusudan, please. It was a delight to have you.
Thank you.
Tomorrow we have SciCon on the campus. It's a science convention where we have stalls and student
Sunday,
conference. Yeah, I mean, if it's you can. It's just a
Email me if I find time. I will.
yeah. It's an invitation. You can if